Hi, my name is Sebastian Witowski, and I would like to talk with you about faster Python. I already talked about that in 2016, and so this is a revised version of this talk, in case you're wondering if it makes sense for you to waste half an hour on try to find a space in one of the other rooms. I changed quite a lot of things. The most obvious change is that I will be talking about Python 3, not Python 2 as it was 6 years ago. But I also removed all the theory. The first draft of this talk would take me 1 hour to present. So faced with the choice what to remove, I decided to ditch all the theory and just keep as many examples as I can. So let's jump right in. Let's look at a simple example. Let's say I want to compute the sum of powers for the first 1 million numbers. I can define a total variable, and then I can go through all the numbers, add their power to the total variable, and finally print that variable. Now I want to check how long it takes to run this code. The red font is not very visible, but I hope you can see it. So for seeing how long it takes to run it, I can use IPython and two of its functions, run, that will just run a piece of code, and time that will tell me how long it takes to run this previous command. This method of measurement is far from perfect, and in the later examples I will use something much more reliable, but it's a simple example and I just want to have the most simple way to give me some number, so please bear with me. And in case you have no idea what IPython is, it's a much better interactive Python shell. So if you want to learn more, I had a talk like 3 years ago. You can find it on YouTube. But back to our example. So I'm running this code, and I can see that it takes 72 milliseconds to run. And I'm using the wall time, which means that I start the timer, I run the code, I stop the timer, and I output the number. Nothing fancy, but I get a number. But obviously, there is a lot to improve here. Let's start small by moving the global variable inside of our function. And doing that takes us down to 63 milliseconds, which is like a decent 15% of speed up improvement, just by eliminating the need to modify the global variable. So global variables not only make your code harder to read and reason about, because first you have to figure out where they are created, but then you also have to figure out where you are modifying them, but they also make your code slightly slower to run. But we can do better. We can use the built-in sum function to actually add the numbers. And to make this work, we will have to change our for loop to a list comprehension. Cool. Our code got a bit simpler, and it's also a bit slower. I mean, just a few percentage of speed improvement, but much easier to read. But we can do one more improvement at this point. If you paid attention at Raymond Hettinger's keynote, you probably can see where this is going. So we can replace the list comprehension with a generator expression. And all we have to do is to remove those square brackets that we had there. And now our code is slower. Is it bad? Well, it depends. Optimization is often a trade-off between speed and memory efficiency. Generator expression has this advantage over the list comprehension that it uses much less memory, but because it does the computation when it's needed. So list comprehension will generate you the whole list at once, and it will use much more memory. So for a very large list, you might actually want to use a code that is a bit slower, but much more memory efficient. And we can actually check that using IPython with the memory profiler extension. So here we can see that the list comprehension will increase our memory usage by around 50 megabytes. But the generator expression, while a bit slower, will have almost no impact on the memory usage. But we can do even better. So let's go back to the example with our list comprehension. Python lists are heterogeneous. It means that you can keep different type of values together, but in our example, we are operating on numbers. And there is a library that is much faster for working with numbers. Since I think half of the people at this conference are data scientists, that's not going to be surprised that we are going to switch to NumPy. So NumPy is packed with functions and data structures optimized for working with numbers. and we can take advantage of that. So we can create an array of integers and then call the power and sum functions from the NumPy library. And if we try to run it, it will improve the execution time by 2 more milliseconds compared to the least comprehension version. Okay, that's not a lot. It's almost as if using NumPy doesn't make sense. Well, it turns out that the problem is not with NumPy, the problem is with my poor simple benchmark. If we try to run the benchmark the second time, we can see that now it's taking around 10 milliseconds to execute my code. That's because my benchmarks are also measuring the execution time of the import statement. And the second time I run it, the import statement is much faster. So that's why I said those benchmarks are pretty terrible, and we will switch to something better in a moment. So as you can see, we got down from 72 milliseconds to around 10, which is a pretty good improvement, but more important, we learned quite a few things on the way. We replaced the global variable with a local one, because global variables not only make your code harder to read, but also a bit slower. We switched to using the built-in sum function instead of reinventing the wheel and writing something from the scratch. You can find a lot of optimized functions in the standard library, especially in modules like itertools or collections. We used a list comprehension instead of a for loop, which is a much more idiomatic way to create a list. And if you're more concerned about the memory usage than speed, you can use the generator expression instead. Finally, we reached out for NumPy, which gives you Python bindings for functions and data structures implemented in C and C++. So you can keep writing your code in Python, and at the same time you can benefit from using those very fast languages running under the hood. So what we just saw was the source code optimization. That is, writing your programs in a way that makes them run faster, hopefully without sacrificing their readability. So in the rest of this talk, I want to show you some more examples of 2 or more ways how to achieve some common operation, and then we will run some benchmark, and I will try to explain why one way might be better than the other. You can find all the code examples that I'm using in this repo. I will also show the links at the end. So here is the setup that I'm using for benchmarking. I'm using Python 3.10.4, which was the latest stable release when I was preparing the slides. I'm setting the environment variable Python don't write bytecode, so I don't accidentally cache any bytecode between my benchmarks. And for the actual execution of the code, I use a pretty standard yet simple way of doing that. So here's how it works. This green part tells Python to run the timeit module, which is the built-in module to measure the execution time of some code. Then the red part tells you, hey, run me this code, but don't include it in the benchmarks. This is where I will usually import some code or maybe set up some initial variables. And this will solve the problem that we have with NumPy, where the import statement was taking most of our benchmark. And finally, in the yellow, I will have a function that wraps the code that I want to execute. And not that it matters much, but the benchmarks will run on this laptop. But, well, the actual numbers don't really matter. I mean, you could be using the same laptop, and then you will probably get slightly different numbers. If I rerun my benchmarks multiple times, they will sometimes be a bit faster, sometimes a bit slower, depending on if there is like some CPU spike from some other processes running on my computer. But what is important is that even if you run the benchmarks on a different setup, the slow examples will still stay slower than the fast examples, and that's what matters the most. So let's say you want to do some action, but you are not sure if it will work. There are 2 common patterns to approach this in your code. You can explicitly check if what you're trying to do is possible and then do this. So let's say we're trying to read a file, and the file might not be there. So you check if the file is there. If it is, you read it, you return the content. But even if the file is there, you might not have access rights to read it. So you add another if, and then the amount of ifs that you have to put there will start growing, but you still don't have certainty that some unexpected problem won't prevent you from reading this file. So there is a different approach that you can try. You can try to do the action, and in case it fails, you can wrap it in a try except block. So let's see which one of those approaches is faster. I have a very simple example. I have a base class that might or might not have some attribute. I'm making a subclass, and in the subclass, I want to access this attribute. But if the attribute is not set, my code will fail. So I can either check if my object foo has this attribute hello before I try to access it, or I can try to access the attribute hello, and in case it fails, I can wrap it in the try except in the try except that catches the attribute error. And if I run my benchmarks, I can see that asking for permission is around 15% slower than asking for forgiveness. I mean, slightly slower, but not some crazy amount. But what if our class has more than one attribute and we still need to check all of them? So this time I'm using a class that is supposed to have 3 attributes, and we still want to check all of them before we perform some action. If we run the benchmarks with more attributes to check, we can see that asking for permission is around 80% slower. So does it mean that asking for forgiveness is always the best choice? Well, let's see what happens if the attribute is actually missing. So here I commented out one of the attributes that we are trying to access. And if I run my benchmarks one more time, I can see a completely opposite picture. Like now asking for forgiveness is almost 4 times as slow as asking for permission. So the tables have turned because handling exceptions takes time. So a good rule of thumb here is to ask yourself, is it more likely that my code will throw an exception or not? If the answer is yes, it will throw an exception, and you can predict what will go wrong, then an if statement is a good idea. It will be faster, and it will much better show the intention of your code. But if you find yourself putting a ton of if statements and just to catch some errors that happens once in a while, and your code already failed twice because you forgot to include some corner case, then maybe it's better to use the ask for forgiveness and just wrap your code in a try except block. Let's see an example of how you can iterate over a collection of items and find the one that's matching some criteria. Let's say I want to find the first number that is divisible by 42 and 43. I could use a naive approach and write a while loop that just starts iterating from 1, or returns me the value if it's divisible, and otherwise it's incrementing the number. While there is nothing very wrong with the while loop, there is a lot of unnecessary code. We are manually incrementing the counter, which feels like we can do better than that. So let's give it a try. We can use the for loop. And inside our for loop, we will use the counter that will keep returning us the next number. And if we measure the execution time of both of those functions, we can see that the while loop is around 25% slower than the for loop. But more importantly, the for loop is much smaller and easier to read. Sorry. So what if someone told you that Python is all about list comprehensions and that for loops are bad, and if you're dealing with lists, you have to use list comprehensions? Let's give it a try. So here I'm checking the first 10,000 numbers, if they are divisible by 42 and 43, and then I pick up the first element from that list. As you can probably guess, using a list comprehension is a terrible idea. We are unnecessarily creating this whole list. We unnecessarily filter those 10,000 elements and then we pick the first one. It would make sense if we wanted to check all 10,000 elements, but in our case, it doesn't make sense. What we want to have here would be some kind of lazy list comprehension. And lazy list comprehension is basically a generator expression. So we can write a generator expression that will filter the list of numbers based on our criteria and then simply grab the first element using the next. Generator expression will do just enough computation to give us the number that we need. And if we benchmark it, it turns out that it's almost as fast as using a for loop. So generator expressions are a great alternative to list comprehensions if you need to evaluate them lazily. They are fast, concise, and memory efficient. But if you want to check multiple conditions with some nested if statements, we could in principle wrap them in like a function and use that function to use the filtering, but sometimes that's just too much, and I personally stick with the plain old for loops for simplicity. While we are talking about lists, let's take a look at another example. Let's say I have a list of numbers and I want to get all the odd numbers. I can write a simple loop that will do the job. And for filtering 1 million of numbers, it takes around 33 milliseconds. But since we are filtering something, there is literally a function called filter in the standard library, so we can use that to simplify our code. And now our code is simpler, but it's also slower by around 50%. So instead of using a filter function, we can try to use the list comprehension since we are constructing a list. And the list comprehension is a clear winner here. We can see that the for loop is around 30% slower and filter is around twice as slow. So in this example, we tried to use 3 different structures, and while the list comprehension was the fastest one, and in my opinion the most readable one, each of the constructs we used actually has a valid use case. So list comprehensions are the obvious choice if you want to build a new list, but if you don't need to have the whole list at once, the filter function is actually quite useful because it returns an iterator. So if we take a look back at the second code example, we can see that we are actually calling a list on the filter, and constructing this list is actually what takes most of the time. So if you need an iterator that will generate the next value only when it's needed, filter is actually a great choice. And finally, we have the for loop, for some people called non-Pythonic. But honestly, there is a limited amount of if statements that you can put in the list comprehension before it becomes unreadable. So if you have like a more complex filtering condition, I would just stick with the for loop. Let's cover one more example with list, and then we will switch gears to something else. How do we check if an element exists in a list? Let's say we have 1 million of numbers, and we want to check if a specific element exists in a list. Again, I can do this with a for loop. I just go through the numbers. If I find the one that I'm looking for, I return true, otherwise I return false. But we can achieve the same results by simply using the in operator. It's much less code, and as you can probably guess, it will be faster. So if we run the benchmarks, I can see that I'm actually checking 3 different scenarios. When the element is at the beginning of the list, when the element is at the end of the list, and when the element doesn't exist in the list. But the results are pretty consistent across the board. We can see that using the for loop is around twice as slow as using the membership testing operator. Okay, that was kind of a boring example. I mean, if you know the in operator, you will not think about writing a for loop to check if a number exists in a list. But we are not done yet. We can do better. Instead of using a list, we can use a set. Lookup time in a list has O(n) time complexity, which means that if the list grows bigger, then the lookup time takes a bit more time. But the average lookup time in a set is constant. So if we run the benchmarks, we can see something very interesting. For the element located at the beginning of a list, the lookup time in a list is only 6 times as slow as the lookup time in a set. But if the element is located at the end of the list, or it doesn't exist, then the lookup time in a list is over 100 times slower than the lookup time in a set. And that's impressive. It would be even more impressive if I wasn't cheating. So the thing is, I did not include converting a list to a set in my benchmarks. I only created a set in the initial code that is not being benchmarked, and then I was doing the lookups. But if you're starting with a list, then you will have to convert it to a set in the first place. So let's update our benchmarks with a function that actually does the conversion to a set and then that does the lookup. And when I compare the numbers now, I can see that membership testing in a list is much faster than doing the conversion from a list to a set just to do this one lookup. So if the element is located at the beginning of the list, then the lookup time in a list is like 40,000 times faster. But if the element is at the end of the list or doesn't exist, then the lookup time in a list is still like twice as fast as the conversion. So to conclude this example, using for loops to perform membership testing is a terrible idea. Using the in operator is usually twice as fast. The average lookup time in a list grows as the list gets bigger, but the average lookup time in a set is constant. So if you already have a list, then converting it to a set just to do this one lookup doesn't make much sense. But if you have a choice between constructing a list or constructing a set in the first place, if you choose the set, you can gain some crazy levels of performance improvement. And one last remark, set is not a drop-in replacement for a list. For example, sets are not ordered. So don't randomly change your data structures because some guy at the conference told you that you're gonna improve your code by 100,000 times. There's this really nice wiki page that shows you the time complexity for common operations in different Python data structures. So I can highly recommend this. Let's talk about creating dictionaries. There are two ways to create a dictionary. One is to call the dict function, and the other one is to use the literal syntax, so just use those two curly brackets. And in many cases, they are equivalent, so you might not give it much thought and assume that they both take the same amount of time. But actually, if we measure the execution time, it turns out that the dictionary is two times faster than, using the dictionary is over 2 times slower than using the literal syntax. And that kind of surprised me, so I decided to dig a bit deeper and see what's happening. So I fired up the disassembler for Python bytecode and looked what happens under the hood. The dis module is what you can use to print the bytecode instructions that will be executed. And even though I usually don't know what most of those instructions means, I can see that the important bit of code is this call function. Okay, that doesn't work very well. Well, that call function. You see, nothing stops you from doing this in your code. I mean, this is stupid, but Python allows you to be stupid. So when you call dict function, Python interpreter has to check if maybe somewhere you have overridden the dict function. But if you use the curly brackets, you're actually using a Python statement. There is no way for you to override it, so Python can directly call the corresponding bytecode instruction. So that's why using literal syntax for creating dictionaries, lists, and tuples is faster than calling the equivalent function. And this module is a great tool if you want to see the bytecode instructions that are actually executed when you run some code. So if you're curious what your code is doing under the hood, you can check it out. Let's say you want to remove duplicates from a list. So here I have a list of 1 million numbers, each of them between 0 and 99. I can write a for loop that will go through the duplicates and append the unique numbers to a new list, and then I just return that list. I could also write a list comprehension that does the exact same thing. And if I measure the execution time of both commands, they take more or less the same amount of time. Except that this is a terrible way to use a list comprehension. List comprehensions should be used to create a list, but in our case, we are using it for the side effect of appending an element to some other list. And the list comprehension will still return us this huge list of nonce that we are immediately discarding. So please don't do that. It's better to stick with a for loop to better show our intentions in this case. But there is a data structure that we already talked about that by definition doesn't contain duplicates. Any guesses? as a set. So we can take our list of duplicates, convert it to a set, and then convert it back to a list. And doing this, it's way faster. Using the for loop is around 50 times slower than doing this list to set to list conversion. But there is one caveat with this method, though. Sets don't preserve the insertion order. So the list that we get back from this list to set to list conversion might have a different order of elements. If we care about that, there is a trick with dictionaries that you can use. So we can create a dictionary with keys taken from the list and convert that dictionary back to a list. This will remove the duplicates and preserve the insertion order. And if we benchmark this, it's still much faster than using the for loop. Now the for loop takes around 28 times slower than the dictionary trick. There is a small caveat though. This will only work with hashable keys, and hashable basically means immutable. So if you have a list of lists or a list of dictionaries, then this trick is not going to work. And I am running out of time, so the last thing I want to show you is that just for fun, I decided to measure the execution time of all those examples with different Python versions. So I used PyEnv to switch between Python versions. So I switched to Python 3.7, I ran my benchmarks, switched to 3.8, ran my benchmarks, and so on. If you want to learn more about PyEnv, I also have a blog post about that. And we can see the results here. So on the left side, we can see the functions that I was checking. On the top, we can see the Python versions. The latest one was 3.11 alpha release because PyEnv didn't have the beta one when I was running the examples. And in the last column, we can see how much slower was version 3.7 versus 3.11. So that's a lot of numbers. I put the most important in bold. And as you can see, Python 3.11 is a clear winner here. Like, there is a lot of improvements here, but also, in general, you can see that when you're upgrading Python versions, there are usually speed improvements. Sometimes there will be like some small degradation, but usually the execution time improves. So what happened in Python 3.11? Well, in 2020, Mark Shannon, one of the core developers, came up with this idea that he can make CPython faster by a factor of 5. And he proposed this idea that there will be like 4 stages. First 2 will focus on like general improvements. Second 2 will try to create a simple JIT compiler. And now Mark is working at Microsoft with Guido and some other smart people. And in Python 3.11, we can see the first fruits of their labor. I think Mark is giving a talk at EuroPython this year, so I'm looking forward to see it. And this is the rest of the benchmarks. You can also find the benchmarks in the folder in the repo. And I have 2 minutes for the conclusions. Okay, so I wanted to have much more examples, but of course I don't have time. So in the repository for this talk, you can see a bunch of other examples. I also kept examples where the code didn't improve in terms of speed, but I also tried to clarify, to explain why it might be better to use something else. And this whole idea for this talk started as a list of articles on my blog. So if you want to get more details about examples that we covered, you can find it there. It's not updated since a year, but I will get back to blogging because I have a huge backlog of things I want to talk about. 1 minute for the conclusions. Do I have 1 minute? Yes, perfect. So source code optimization is often the last thing you will think about when you have some performance issues. And that makes sense. I mean, no one will start optimizing the code by rewriting it unless you have like terrible code. But source code optimization is not something that you should be doing when you have performance issues. It is something that you should keep in the back of your head when you write your code in the first place. Just being curious about which code structure is better will lead you to understanding Python better, understanding which data structure is better, and sometimes understanding what your code does under the hood. You can replace a for loop here and it will give you like 20% speed improvement, but if you replace it here, change the data structure there, do something else there, then suddenly your code is twice as fast. And please, please, please don't sacrifice readability for some small performance gains. Fast code is good, fast code that is hard to read is bad. Thank you, my name was Sebastian Witowski. You can find all the links here, and we don't have time for questions, so I'll be outside